Dear students, the next topic is design of asynchronous counter. Okay. So we already saw the design of synchronous counter and now it is the design of asynchronous counter. Okay. As already told, the asynchronous counter is one of the counters where the flip-flops are connected in such a way that output of the first flip-flop drives the clock of the next flip-flop. Okay. And one other important point which I told you was it is not clocked simultaneously, right? That is one of the main speciality of the asynchronous counter is it's not clocked simultaneously. Okay. So, and we know what exactly the clock does. So it is a register where the counting it counts the number of clock pulses arriving at the clock input, right? So let us design an asynchronous counter, which is also called as the ripple counter. Okay. So let me design this asynchronous counter with the help of an example. Okay. So the problem is design a BCD ripple counter, okay, using JK flip-flop. Students, as I told you, once they ask us to design any circuit with the help of given flip-flop, we are supposed to use the same. Okay. And one more thing I want to say here is, in case of asynchronous counter, it's quite simple when compared to the synchronous counter, because here the counting sequence is as normal as the synchronous counter. Here we do a major task of assigning the output of reset logic. That is, we assign the positive or correct clock pulses. That is, we count the state of the clock, and whichever clock has the valid output, we say that it has a valid states. Okay, I'll just explain you all with the example, it will be more clear to you all. Okay, so whichever state is not valid, we mention it as not valid. Okay, so that is a major task we do in a asynchronous counter. Okay, so here there are totally 5 steps. The steps are very easy. So step 1 is, we'll determine how many number of flip-flops to be used. Okay, flip-flops to be used. Second step is to determine what flip-flop to be used or which flip-flop to be used. Okay, that's already given in our problem. That's nothing but JK flip-flop. Step 3 is, we will have to write the truth table. We'll have to write the truth table for the counter. Okay. Then step 4 is, we'll have to write or we'll have to derive the reset logic. Okay, the reset logic is nothing but the K-map expression where you get, okay, for the output. And the last step is, we'll have to draw the logic diagram. Okay, so these are the 5 major steps of design of asynchronous counter. Okay, now let us consider the first step. Okay, now we'll have to decide how many flip-flops to be used, and since it is a BCD ripple counter, we know that the BCD numbers valid state is from 0 to 9, right? So when it is 0 to 9, the total number of states that we get is 10, right? Right from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So these are the valid states of a BCD counter, right? So these valid states, if you count, you will get the number of states is totally 10. Okay. So if I have to decide the number of flip-flops to rise to the power of n greater or equal to total number of n, that is states. So it is to rise to the power of n, to rise to the power of 4 is greater than 10, right? So 4 will be the number of flip-flops to be used, correct? So since they mentioned as JK flip-flop here, the sequence will be JAKA, JBKB, JCKC and JDKD, right? Okay, now let us design. The next step is to derive the truth table of the counter. Okay. Now the clock, the first column will be clock. Okay. The first column will be clock. The second column will be our inputs. Okay. And the last column will be something that is output of reset logic. So let us say that output is Y. Okay. So this is the outline of my asynchronous design of counter. Okay. Now clock is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. These are the valid state because it is a BCD number. In case if I ask you to design a mod 6 ripple counter, then 0 to 5 will be your valid state, correct? And 6 and 7 will be an invalid state. Clear? Anything for that matter has to be designed in the same methodology. Now 0 to 9 is my valid state. When I say the 4 is the number of flip-flops, we know the combinations of inputs that is possible because we have discussed all this in the previous basic sections. Okay. So when it is 4, the combinations are, as you know, it's from 0 to 16, right? So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then you have 10, 11, 12, 13, 14, 15, right? So those are your invalid state, but you can very well mention its combinations. Okay, so it is 1 0 1 0, and it is 1 1, it is 1 0 1 1, 1 1 0 0, 1 1 0 1, it's 1 0 1 0. 1 minute, here it is 9. So 10, 11, 12, 13, 14, the last one is 15. Yes, so 10, 11, 12, 13, 14, 15. Okay, so we have mentioned all the combinations of numbers. Clear? So here what we have to do is, so the counting, since it is a BCD ripple counter, the valid state is from 0 to 9. So you just mark blindly a 1 across all the valid state. As I told you, since it's a BCD ripple counter, your valid states will be from 0 to 9. That is a logic 1 for 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So rest of all the combinations, okay, it's going to be your zeros. For rest of all the combinations, it's going to be a 0. So the valid states are for the clock 0 to 9 is said to be our valid state because it counts from 0 to 9 being a BCD ripple counter. So this is said to be as valid state, and this is said to be as invalid state. Invalid state. Okay, so we have completed our truth table, and the next is, let me turn the page, and the next is the reset logic. Reset logic, as I said, is nothing but the K-map expression for the output. Okay, so since it's a 4 combination, that is, you will have 16 cell K-map you will have to draw. So the 16 cell K-map is something like this. So you have A, B, C, D, the inputs. You have 0, 0, 0, 1, 1, 0, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. Correct? And if I have to draw the expression for output using the inputs of clock, for output I have 1, 1, 1, 1, 1 1 1 1 0 0 0 0 1 1 0 0. Okay, so this is for your output 1. Now if I have to group it, it's very obvious. This will be my first group and this is going to be my second group, correct? So my expression for y will be, for this group, the common term is a bar, plus for these two groups it is, the common terminology is c bar, and here it is b bar. So it's b bar and c bar. So this is my reset logic. Okay, the last step is we'll have to draw the logic diagram. It's very easy because we'll have to draw for the output, but the only thing is here, since we have 4 flip-flops, you have to draw the flip-flops. Okay, and here it is JA, KA, here it is JB, KB, JC, KC, here it is JD, KD. Okay, now as I told you, the main function of asynchronous counter is, it is connected in such a way that output of the first flip-flop drives the clock for the next of the flip-flop, right? So I'll have to I have to signify the asynchronous counter. So this is my clock pulse. Okay, so since it's an asynchronous counter, so let me do the basic justice. Okay, so this is the clock, and you have JA, JB, JC and JD. Now I have to connect A bar, B bar, plus C bar, right? So these two will form my AND gate and this will form my, so this is my output which is given as Y, right? Okay, see, you have to understand one thing. The reset input, that is the CLR of each flip-flop, is active low input by making clear input of all flip-flops connected to 0. We can reset the counter. Thus, the reset logic is designed in such a way that for the invalid states y is equal to 0 and for the counter resets. Okay, and that is why we connect this clear to zeros. Okay, and now your JA, your JB and JC and JD will be connected to a logic 1. Okay, so your most significant byte, but we can say this, and this will be your LSB. Okay, so this is the logic diagram of BCD ripple counter, and this completes your design of asynchronous counter, the ripple counter. This is having the number of states 10. Okay, if I ask you to design the ripple counter, say of state 6, then the valid states of counting will be from 0 to 5, and 6 and 7 state will be invalid. Okay, so the logical valid states you will put, or you will assign one only for the states 0 to 5. Remaining 6th and the 7th state you will consider it as invalid state, and rest of the procedure will remain the same. I think hopefully you have understood the design of asynchronous ripple counters. Thank you.